Greetings, fellow mathematicians. We're going to take a look at two tips that are going to help with finding inverse Laplace transforms. Now, to get started, we have to understand what we're doing. Earlier in your differential equations course, you were given a function of time, t, and asked to find the Laplace transform. Now, we're going to be going backwards to our problem. Given the function of s, the function of frequency, we're going to go backwards and figure out what the function of time is. Now, this gets very complicated. The technical way we should be defining an inverse Laplace transform requires complex analysis. That's not available yet in your differential equations course, so most of your work in going backwards from f of s to f of t, that's done with a partial fraction decomposition. You take your f of s, perform a partial fraction decomposition, and then you'll typically get a bunch of partial fractions similar to these over here in the f of s column. Now, the two tips that we're going to address, they're going to help with when you do the partial fraction decomposition. There's some constants, n factorial, b's, a's, that might be missing. And the two tips, multiplying by 1 and adding 0, will fix what to do if those constants are missing. So we're going to take a look at 4 examples here to illustrate how we use these two tips, how we multiply by 1, and how we add by 0. The first two are rather simple. The second two require a little bit of work, but we'll point out that momentarily. So let's get to the first two and illustrate how we multiply by 1. The first two problems here are very straightforward. Now, whenever you start calculating inverse Laplace transforms, you want to start by looking at the denominators. So if we go to our first example here, our denominator contains only a power of s, and that's very easy to match to the first Laplace transform pair here, or this f of s. Now, we need to figure out what the value of n is, and if we take a look at our power, it's s to the 4th power. The formula has the exponent as n plus 1. So if it's not obvious, you solve a simple equation, n plus 1 equals 4. And that implies the value of n that we're going to be using here is 3. All right, we have that determined, but notice we can't directly transform that back and match it because we would need in the numerator here, if the value of n is 3, we would need a matching factor of n factorial in the numerator. So we're missing that, and the trick that we're going to do is we're going to multiply by 1. We need a factor of 3 factorial, or n factorial. We can't just put it in the numerator, but we can put a factor in the numerator and a factor in the denominator. So let me write this out. We're going to multiply by 1, where we'll think of 1 as 3 factorial divided by 3 factorial. And here we can just rearrange it. I want this 3 factorial in the numerator of that fraction involving s. The 3 factorial in the denominator, I can just pull that out front. So I'll go ahead and rewrite this as 1 over 3 factorial. That's the factor in the denominator that we don't need. And I'll move that factor of 3 factorial into the numerator to write this as 3 factorial over s to the 4th. And at this point, we are done because that fraction, 3 factorial divided by s to the 4th, that now matches exactly that inverse Laplace transform f of s, and we can transform it back directly using the value of n there as 3. So directly from here, our function of time, the little f of t, we just have a constant multiple out front, 1 over 3 factorial. And now the 3 factorial divided by s to the 4th, that's going to transform back as t to the 3rd power. And that's it. The key here was that step multiplying by 1, 3 factorial divided by 3 factorial. You'll find in other problems you're going to attempt, what you multiply and divide by changes, but that comes from the missing factors, but it's always going to be multiplying by 1, something divided by itself. All right, that one was pretty straightforward. Let's take a look at the second problem. This one is also straightforward, but just a different denominator. So we go to our Laplace transform table, and it looks like it's going to match the second entry. And just be careful, between your sine and cosine transformations, your numerators have a subtle difference between them. Your sine transforms to have a constant b in the numerator, but cosine transforms to have the variable s in the numerator. So just be aware of that. Since we have a constant 1, we're going to think of it matching this f of s, or this Laplace transform pair. Now the problem is we have a constant in that denominator, s squared plus b squared. So we're going to think of 4 as b squared. And that means we're going to identify the value of b to match this formula as 2. Well, the same problem in the first one exists. We're missing a factor of 2 up there. That's no problem. We're going to multiply by 1, thinking of 1 as 2 divided by 2. So let me just rewrite this. I'll make this step explicit. We're missing a factor of 2. In other words, we're missing a factor of b. So we're going to multiply and divide by that. Multiply and divide by 2. And same thing as the first problem. We want this 2 moved into the numerator. The 2 in the denominator, you can just pull that out front. And you can write this as 1/2 times 2 divided by s squared plus 4. And now this matches exactly the form you would want in your Laplace transform table here. So we can transform this back where we're using the value of b as 2, and it looks like we get our little f of t. The factor of 1/2 just stays. And the 2 divided by s squared plus 4, that transforms back as sine of 2t. And that's how we use the trick of multiplying by 1. That's going to be used where we have factors that are missing in the numerators. Like here in problem 1, we were missing a factor of 3 factorial. And in problem 2, we were missing a factor of 2 in the numerator. All right, next up, we're going to get to the trick of adding 0. For the third problem, we're going to start by trying to match the denominator to an existing Laplace transform pair. Now, the problem is, this doesn't match anything exactly as written. So you have two options. You could try to factor your denominator and go through a partial fraction decomposition, but you'll find this denominator doesn't factor. If that occurs, you might be able to match one of these Laplace transform pairs, specifically the last two, by going through the technique of completing the square. Now, I always like to remind my students of a very nice and simple way to go through completing the square, where you actually add 0. This might be different from how you know to complete the square, but let's go ahead and take a look at how we complete the square by adding 0. So let's start with our denominator just by itself. S squared minus 4s plus 13. And the way I like to advocate to complete the square is we take our middle coefficient. In other words, if we think of this as being a quadratic expression, as squared plus bs plus c, we're going to identify b as -4. And we're going to add and subtract b over 2 squared. All right, so if we go ahead and calculate what we're going to add and subtract, that's adding 0. Take b divided by 2, negative 2, square it, you get 4. We're going to add and subtract 4 here. So let me just go ahead and write that here. S squared minus 4s. I'm going to add 0. I'm going to add 4 and then immediately subtract 4. All right, and again, just make sure you see that. We're adding 0, 4 minus 4, which is totally allowed. And what this does for you, usually the first 3 terms there, you can write them as a perfect square, and the first 3 terms do factor. And it looks like that's going to factor as s minus 2 squared. And then you have your remaining numbers, negative 4 and 13. Those can be combined to give 9. All right, now here, when your denominator doesn't factor and it doesn't obviously match any of the Laplace transform pairs, you complete the square, and that involves, as I teach it, adding 0. Now, if we go ahead and use that here, should be able to easily match one of those Laplace transform pairs. We'll write our denominator as s minus 2 squared plus 9. And that does look like this Laplace transform pair. And again, be careful with your numerators. You either have a constant b or an expression involving s minus a. And since we have in our numerator 1, we're going to try to identify it as this one. Now, like happened in the first 2 problems, we're missing a factor in the numerator. We know what to do in this case. We're going to multiply by 1. We're going to identify the value here in the denominator as b squared. So if b squared is 9, that's going to imply b is 3. And right there, inside that completing the square term, we're going to identify a as 2. All right, the only thing we need to do is get a factor of 3 up there, but we can do that by multiplying by 1. And I'm going to multiply and divide by 3. And like the first 2 problems, I'll move the 3 into the numerator. The 3 here, I'll just move that out front. So we'll write this as 1/3 times 3 over s minus 2 squared plus 9. And now we should be able to match it exactly to the form that we need, where we're going to identify a as 2 and b as 3. And the inverse transformation should fall into place. And it looks like what we get here, if we basically just plug in directly here, we have a factor of 1/3. And we get e to the at, where a is 2. So e to the 2t. And then we get a sine of bt term, where b is 3. All right. Again, we used completing the square here. And important to see, you can complete the square by adding 0. The third problem here, this is a warm-up for problem 4, where there's a little bit more work, and we're going to see the technique of adding 0 for a different reason. The fourth problem here is a little bit more work, since we're going to need both tips. We're going to multiply by 1 and add 0 at different points. Now, we're going to start by trying to factor the denominator, but it doesn't factor. So the only hope that you have for getting it to match anything in your Laplace transform table Specifically, the last two is to go through completing the square. So let's go ahead and go through that first. We'll take our denominator, s squared plus 6s plus 25. And we'll actually add 0 here, the way I like to complete the square. Take your b coefficient, 6, divide it by 2 to get 3, square it to get 9. We're going to add and subtract 9. So think of this as s squared plus 6s. We're going to add 9 and then immediately subtract it. And what you should find is probably always the first 3 terms can usually be written as a perfect square. And here you can factor the first 3 terms as s plus 3 squared. All right, and your last 2 numbers, you can combine those together, -9 and 25, to get 16. All right, so let's go ahead and put that in our denominator here. S plus 3 squared plus 16. And our numerator is 2s plus 8. All right, now our denominator matches exactly these last 2. But we need to pay attention to our numerator. And now our numerator contains the variable s. So we should be thinking we're going to try to match it with this last Laplace transform pair. Now the problem when you complete the square, when you have an s variable in the numerator, you have this term, s minus a squared in the denominator. But in order to have the transformation match exactly, you need s minus a in the numerator. But what we have in the numerator is 2s plus 8. How do we get the numerator to match? Well, we're just going to use a simple trick here, or tip. We're going to add 0. I'm going to take the variable s and to match it with my denominator, which is s plus 3 squared down here, let me go ahead and add and subtract 3. So we're going to think of s as s plus 3 minus 3. We are adding 0 here, so this is technically allowed. Now, how we actually use that here, let's go back to the way this is written, and let me just go ahead and insert a set of parentheses around the variable s in the numerator. And I can just plug in now, or add 0 inside those parentheses or brackets, and it basically falls into place from there. It's certainly okay that there's a factor of 2 out front. We'll take care of that in a moment. So let's go ahead and add 0 inside those brackets. We have that factor of 2 out front. We took the variable s and added 3 and immediately subtracted 3. We still have the plus 8 outside of the brackets. And we're keeping our denominator the same as what's above. S plus 3 squared plus 16. Now, you have to be careful here. That factor of 2 out front, we are going to distribute it, but we have to be careful and not distribute it too much. What we're going to try to notice is we want this s plus 3 to match the s plus 3 squared in the denominator. Now, we're going to distribute the 2, but we're going to think of the first 2 terms here, s plus 3, as being one quantity. That's going to allow us to match part of that to this last Laplace transform pair. we can take that factor of 2 and also distribute it to the negative 3, and that's going to allow us to match the other related Laplace transform pair where we have just constants in the numerator. So let me go ahead and distribute the 2 to the part in parentheses here, and I'm going to distribute the 2 to the negative 3. So I'll write this as 2 times the quantity s plus 3, and then minus 6 plus 8. We're going to keep the denominator the same. And now we can basically split this into 2 separate fractions. From here, you can combine the 8 and negative 6 to get 2, and that will give you a constant in the numerator. The other part we have here, the s plus 3 in parentheses, we're going to use that to match this numerator in the last Laplace transform pair. So let me go ahead and split this into 2 fractions. I'm going to pull this 2 out front. And we'll have in our numerator here s plus 3. And that's over your denominator. S plus 3 squared plus 16. And we have negative 6 and 8, which combine to 2. Let me go ahead and write that as a separate second fraction, thinking of that as 2 over that denominator. I'm going to pull the numerator out front. And now we should be able to adjust any missing factors. Now, if we take a look at the first fraction that we have here, that matches exactly the last Laplace transform pair. We're going to identify the value of a as negative 3, because keep in mind here, we have it as s plus 3 squared, but the formula contains s minus a squared. So here, a is going to be negative 3. And your value for b, that should be 4. All right, now your second fraction here, this is one where we're going to have to maybe adjust any missing factors. Since we have b identified as 4, we would need a factor of 4 in that numerator there. Now there's 2 ways you can do this. Here I like to pull any constants that I don't need initially out front and then adjust them later. You could certainly keep the 2 in the numerator. If you do, to get a 4 in that numerator to match here, you'd only need to multiply and divide by 2. Here, since I pulled the factor of 2 out, let me go through the trick here of multiplying by 1, where we'll think of 1 as 4 over 4. This is a nice technique in case you don't have a nice number working out there to 2, like negative 6 and 8. If you have something a little bit weird, like 7, just pull that out front and then adjust your factors like we're used to here, multiplying by 1. All right, now this should fall into place. I'll take this 4, move it to the numerator, and the 4 in the denominator, I'll just pull it out front. 2 over 4, that'll give me a half. So keep in mind here, you have a factor of 2. We're going to keep this as is temporarily. We're almost done. We have that as s plus 3 over s plus 3 squared plus 16. And again, I'm going to pull the 4 in the denominator out front. 2 over 4, that becomes a half. And the 4 here, we're going to think of that as being in the numerator. So let me move it into the numerator. And keep the denominator the same. And now we're basically done both fractions match exactly the last two Laplace transform pairs, and it is a lot of work, but it's all very straightforward, tedious work, provided you know how to implement it. Just to trace back, most of the work occurred here, replacing s with s plus 3 minus 3, and the rest of it was just expanding, distributing, and now at the end here, adjusting missing factors. So we should be able to transform to f of t, or little f of t, I should say. And we have a factor of 2 out front. And we're going to identify the two values we want, a as -3 and b as 4. And we'll get combinations of exponentials times sines and cosines. So it looks like we get here e to the -3t. And that's going to be, for that s minus a in the numerator, s plus 3. That's going to match an exponential times cosine. All right, and the last fraction, we have a factor of 1/2 out front. And now this fraction, that's going to match exactly the exponential sine term. So 1/2 e to the -3t times sine of 4t. And that's it for this one. Again, most of the work is here, algebraic manipulations, multiplying by 1, and adding 0. Hope you learned a lot in this video. I want to keep it short, but at the same time, I don't want to cut out any detail. So hope you're able to get everything you need from this. If you enjoyed the content, support the channel, hit that subscribe button.